has an out-of-bag misclassification error of about 24%. What about random forest? Okay, random forest is different in nature from bagging because random forest, to my understanding, does not use different resamples of the training and test set. What happens, though, how random forest is different, and what makes it perhaps more powerful is that when you grow a random forest with so many trees, at each split in the tree, each branch in the tree, it does not exhaustively consider all of the variables. It is limited in how many variables it considers. And the choice of those variables, the choice of that subset of variables that it considers, the predictive variables that it considers to be the choice, the variable to use at the first split, it's a random event. Or said a different way, with each tree that is grown, with the first split, there is a subset of the prediction variables that are considered, but in each tree, it's a different subset. It's slightly different. And I wish I was more intimately familiar with the algorithm to tell you exactly how it hones in on a particular subset of, say, 5 variables, but it does, and they're different with each tree. But then within that small subset of variables, it chooses the one that has the most bang for the buck, that creates splits with the greatest purity. And but what you get as a result, even though you're growing each of the, say, 100 trees in the forest from the same training test set, each tree will be at the root node at the first split will split on a different variable many times. So you get the same effect that you get with bagging in that the trees are diverse. The trees, they don't repeat themselves. If you have an extreme misclassification, it's unlikely to occur the next time because it is, it's iteratively going through these small subsets of variables and choosing one. So it smooths out the errors. And you'll see here we're saying we have the same modeling formula, same training data, and we're calling for the importance to be explicitly captured. And again, P3, we could look at P3. It's got a lot more in it than just this. But you'll note that, in fact, let's do that. Let's take a look at this. What is actually in the fitted object? Random forests tend to be more numerically oriented. That is, they tend to rely more on numerical measures of the error, the misclassification error, rather than just rules per se. You don't have a set of rules, in fact, because each tree is different. So it makes no sense to print, a set of rules for each tree. They're all going to be different. But it uses 2 separate metrics for misclassification error. One is just simply tied pretty tightly to the percentage, the number that are misclassified, and the second is tied to the so-called Gini, the Gini index that we kicked around. It's a diversity index. I believe I sent out an email. Somebody asked about the background. I went out and looked at it. It's tied to area under the Lorenz curve. There are formulas. There is a specific algorithm and formula that I referenced there in Wikipedia. But the bottom line is the Gini index also is less tightly coupled with error rate, but that's really what it hones in on. So we run this and we get P3, and then we're going to plot it. And note again, when I say that the random forests are more empirically oriented or numerically oriented, even the plot, what we have here are plots of each of the 6 levels of the classification variable. And I don't have a legend, so I don't know which one is which. Note in RStudio you can zoom things. A zoom is a static plot. It's not actively rehearsing or actively interfacing with the program. So it's just like a picture. But one thing you can see from this error plot, which is just from 0 to 1, it's a standardized error for each variable, is that as the number of trees grow, the misclassification error for each of the 6 classes tends to fall off, tends to decline up to a point. So, and that's one of the benefits of having this plot. You can see where you should stop growing trees, which for this one I guess would be right about here, 150. Growing trees can be very labor intensive, especially if you have a lot of predictive variables. So that's the plot. It also captures and reflects out-of-bag error rates, but for each category, each class of the target variable. So, and there are 2 global variables, as this says, the mean decrease in accuracy in all of the classes, and also the mean decrease in the so-called Gini index, based on that Lorenz curve. Okay, so we can plot these. Here we can compare those. We can compare those 2 accuracy measures side by side, and let's give it a little room over here to plot. And so we're going to set up the graphics frame so it'll draw 2 bar plots in the same device, same frame. And there's the importance just on decision accuracy. That is, it's highlighting for each of the predictive variables which ones are more important, important in terms of correctly classifying the levels of the target variable. And if we look at it for the Gini index, let's zoom them so we can see it a little better. You find they're pretty closely aligned. MG, whatever that is the most important predictive variable in terms of correctly predicting the classes, whether you measure that accuracy as decision accuracy or whether you measure it as the Gini index. And the rest of these, there are some differences, but the rest of them they're pretty closely aligned with each other, which further supports the notion that the Gini index is tied to classification error. Okay, so, but which approach is better? How can we tell? We got a computed out-of-bag estimate for the error rate with the aggregation bootstrap with the bagging approach, but we don't have one readily. We could infer it from the plot. We saw the plot up here. These are the out-of-bag error rates. Here we want to reset the graphics frame so we can see that. These are the out-of-bag error rates for each of the target variable levels. But how do we do a direct comparison? Well, one way you can do that is with the IPRED package. And IPRED has a function in there that's called est error, or error est. So let's do that. So we can compare them all side by side. And so first of all, we create this data frame just so we can look at it visually. It's really not that important for the processing of the comparative errors, but note what we're doing. We're creating a data frame where truth, this is the actual type. This is what we're trying to classify. So the first column in this data frame will be the correct classifications for each record. The second one will be the tree predicted classifications, the second column. The third column will be the bagging predicted classifications on the test data, and the fourth one will be the random forest. So it gives us a means to just eyeball it and try and get a sense out of which technique is doing better or worse. Now, I didn't set seed, so every time you do this, you're going to get slightly different results. And the 10%, this is the test data set. So these are the actual classifications for this data set, and this is what the tree predicted, and this is what bagging predicted. Bagging looks pretty good to me. It looks like almost a 1-1 fit, actually. And there's the forest predictions. But we can test it more strictly, more precisely using this AirEst function. And so that's what we do. We call AirEst. Well, first of all, we have to load iPred. Need to do a couple of things. We load up iPred, and I think I did. And we're going to wrap it in this myPredict function. So we need to load this function. And when I say wrap it, you notice myPredict, our part, it's predicting, it's returning the predictions. And AirEst is in iPred. So if I did indeed load the iPred package, this function will run, and it seems to be. And it's doing it 100 times. With 3 different models, still pretty fast. Okay, and we see that the tree, the single tree had an error rate of about 33%, bagging 28%, and the forest was better, which is often the case. I ran this exercise several times, though, and a few times bagging came out on top. So it's quite possible. But in this case, forest beat it hands down. In comparison, let's look at the same error comparisons, error estimates for these techniques using the iris data. So we'll run that. And it's thinking. And actually the tree, okay, this is what I mean about the luck of the draw. Bagging was the worst one. And forest was the best, and the single tree was kind of in the middle. Okay, so that's that.